That's the question we're trying to answer ultimately, right? Is, how do these basic laws and these basic particles come together to make this really rich and complicated and beautiful universe that we live in? That's one of the big mysteries. And, we don't know the answer to that. But we have learned a lot, right? We can speak with some confidence about the origins of the universe going back to a trillionth of a second after the Big Bang. And that's kind of extraordinary, right? If you think 100 years ago, we didn't know anything really about the history of the universe.
I very much enjoyed our first conversation, and I remember we covered so many interesting topics, from the Big Bang to the mysteries of particle physics to even religion. And you might even remember I brought up the famous pale blue dot image, at some point. So almost every single topic that you couldn't think of, we got to discuss in our conversation. But there are still some subjects left, so I thought it would be great to have another one. I'd like to start off by asking you this very big question. I remember reading this wonderful article that you wrote for The Guardian. It was titled, I guess, "Are we about to discover a new force of nature?" Right? And in it, you explore this possibility that we might be on the verge, of discovering a new fundamental force. Like so far, we've been able to measure four of these forces, right? Electromagnetism, gravity, and two nuclear forces. But that would be like a fifth fundamental force. Would you say that since then, have we moved any closer to such a discovery? And for example, when people discuss issues such as the Hubble tension, do they still see it as potential evidence for a new force of nature? Maybe has our thinking changed on that? Have you think about this question today as a particle physicist?
Yeah, I mean, it's a good question. I don't know is the answer, but I think the evidence that we might be is still there. So we have evidence both from particle physics and from cosmology. And the particle physics anomaly, the most interesting ones I think that are still around are these anomalies that we are seeing at the Large Hadron Collider at CERN, and in particular on the experiment that I'm a member of, LHCb. And we look at these particles called beauty quarks, which are also known as bottom quarks. Actually, more usually they're called bottom quarks. And what we have seen in these particles, these beauty particles, they're created in the collisions at the LHC in large numbers. And I'm particularly interested, and many of my colleagues are interested in studying the very, very rarest decays of these particles. So if you make a beauty particle, on average, it lives for like 1.5 trillionths of a second. So very, very short amount of time. But in particle terms, that's quite long. So you have this very short-lived thing, and then it decays and it turns into other types of particles. And there are some decays that are very common that happen most of the time, and then there are some that are extremely rare. So they might only happen once every million beauty particles might decay in that way, or fewer. And for many years now, we've been seeing disagreements in the properties of some of these rare decays compared to what theory predicts. So we have this theory called the standard model of particle physics, and it tells us how often these decays should happen, and it tells us that, what directions the particles should go in and how they should be distributed and various other things. And there are a number of measurements that are in quite strong disagreement with the standard model. Now, the question is are these disagreements, these anomalies, really evidence of something new? Because one explanation for this is that there is some force, some additional force, a fifth force, as you suggested, that is interfering with how these particles decay and changing the properties that you measure. And so this is this anomaly could be an indirect clue to something else out there in the universe, some new field that we've never seen before, presumably also some new particles that we've never seen before. But with any anomaly, there are always a load of boring explanations that you have to eliminate before you can conclude that you've really discovered something new. And, boring explanations include things like you messed up your experiment, you just made some mistake, or there's a mistake in your theoretical prediction. That can also happen. Or there is, it's basically just statistical fluke, that it's just random luck that you got this result and it's actually not statistically significant. I mean, we can kind of eliminate two of those three, but the one that we're still unsure about is whether our prediction in the standard model is right. And that's because the prediction involves contributions from things called quarks and gluons. So quarks and gluons, these are the particles that make up nucleus of every atom that make up protons and neutrons inside the atomic nucleus. And the theory of quarks and gluons is very, very difficult to calculate, famously very difficult to calculate. It's possible the anomaly is actually down to the fact that we don't know how to calculate the influence of quarks and gluons properly. Or it could be there's a fifth force or some new set of particles. And the answer is we don't know. And we are making more measurements and theorists are improving their techniques. So we hope in the next few years that we will eventually be able to settle this debate one way or another. But it's still an unsolved problem. It's very interesting and it's exciting because, when you have attention like this, that motivates you to do more science. But honestly, we don't know is the answer to that one. And then I think in cosmology, like when I spoke to you, I think it was around the time that my second book had just come out, Space Oddities, which is all about anomalies. And one of the things I talk about in the book is this other anomaly in the other end of physics, at the cosmological scales, which you talked about, the Hubble tension, which is a disagreement between how fast we expect the universe to be expanding according to the sort of standard model of cosmology, the Big Bang and the evolution of the universe, and what we know about the properties of the early universe. That theory combined with measurements of the light from the Big Bang tell us how fast the universe should be expanding today. And when we measure it directly looking at nearby galaxies and particular types of stars like supernovae and variable stars like Cepheids, you get a tension, you get a disagreement, which is now over 5 sigma. So these two results are really in very strong tension with each other. And again, this is still an unsolved problem. We don't really know why, and there are lots of explanations. Like it could be potentially a new force, maybe. Some of the more popular explanations are things like dark energy, which we know exists from cosmology. It's this kind of invisible, repulsive force that permeates the universe and causes the expansion of the universe to accelerate. So it's kind of dark energy basically is pushing galaxies further and further apart from each other, making space expand faster and faster. It could be that dark energy is actually not constant. There's the standard cosmological model says that dark energy is a constant, just stays uniform throughout space. If it varied through the history of the universe, then that could perhaps explain these sorts of tensions. And there are many, many other explanations in the market. So these anomalies are very interesting. There's something, I think in cosmology in particular, it's got really, really acute, but there still is not really a clear explanation for what's happening. But that's kind of when science is most exciting, is when you have a big mystery to solve. In some sense, when you solve the mystery, that's great. But well, then you've solved the mystery and you have to think about something else. So yeah, it's still up in the air.
This question might make you feel a bit depressed, as a practical physicist, because for many years there was a lot of hope that the LHC, the Large Hadron Collider, it would uncover evidence for things like dark matter, supersymmetry. But obviously, so far we haven't seen anything right with the LHC that goes beyond the standard model. Do you find that frustrating, or do you remain optimistic that maybe with the upgraded version of the LHC, it's expected to receive this major upgrade by the end of this decade, right? The LHC, and it will be able to accumulate much more data, right? Like the LHC could still find something like dark matter, or how do you feel about it?
I think there's several different answers. I mean, as a human being, the honest answer, I suppose, is, particularly in the early days, when the LHC switched on in 2009, 2010, there was a lot of excitement, and that lots of new stuff might be discovered, from the Higgs boson to dark matter, microscopic black holes, dimensions of space, supersymmetric particles, all kinds of stuff that we hoped we would see. And what was found was the Higgs, and that was really exciting. But as you say, no new particles beyond the Higgs boson have been found, and the Higgs boson was expected based on the standard model. So we have these big unsolved questions in fundamental physics, like the nature of dark matter. Why is there matter in the universe at all? And the LHC so far hasn't really given us any clues as to what those explanations are. What it has done very successfully is told us what the explanations are not. So it's killed off lots and lots of theoretical ideas, which is valuable. So there's not like there's been no progress. We've learned a huge amount from the LHC. We've learned a lot about the standard model, a lot about the Higgs boson, about quarks and gluons, but also ruling out these theories that had been around for a long period of time. But honestly, I think, people have been disappointed, I think, in the sense that there was, it would obviously have been great to discover a whole new sector of fundamental particles and have a mystery to unravel and details to do. I mean, even by 2015, 16, that picture was becoming quite clear. And I think people have now resolve themselves to, actually making new discoveries in fundamental physics is hard. And I think, when I started, I was a very young PhD student at the time the LHC switched on, which was some time ago now. If you're kind of new to the field, perhaps you don't appreciate how hard won new discoveries have to be. And like big new discoveries do not come along every year or even every decade, right? I mean, it can take a long time, and you have to really just kind of you have to remain hopeful and optimistic, but you have to be like diligent and dogged, and you just have to keep going. So I think, what we have with the LHC is the best machine we are going to have for the next 2 decades in terms of exploring the subatomic world. It's the best chance we have of learning something, and we have to exploit it to the full. If you just gave up and said, oh, we haven't found anything, or, there's no point, you don't know what's around the corner. And that's the thing. Nature can surprise you in all kinds of ways. So what we have to do is give ourselves the very, very best chance we can of uncovering something if it is out there. And as you say, so the LHC has just switched off, actually, just as of the last week or so. And we are going into this long period called Long Shutdown 3, which will involve this major upgrade to the machines. This is a massive project to replace significant parts of the LHC in order to increase the intensity of the collisions by about a factor of 10. So when it restarts at the end of this decade, we will be able to collect data at a much, much higher rate across the different experiments. And that will give us a new opportunity to see particles. So it could be that these dark matter particles or supersymmetric particles or something you haven't even thought of is out there hiding, and it's just very difficult to see. It's kind of hiding amongst the ordinary standard model particles that get produced ubiquitously at the LHC. And so, but by getting more and more precise, more and more data, we've got a better chance of eking out these signals. So yeah, you have to kind of remain focused and determined. But I think that the fundamental fact is that we know there must be new physics, there must be new particles, and the LHC is the best chance we have of finding them. And so we've got to exploit this machine to the full. And there's, people are obviously talking about the next generation of machine already, about what comes after, but there is no guarantee that such a machine gets built. I hope something is built, but in the meantime, we've got the LHC, it's there, it's this amazing facility, we've got to make the most of it.
Would you say that particle physics it has in a sense hit a wall, meaning that we become too successful, right? Like you said, the standard model is so incredibly successful ever since it was put in place, I guess in the 1970s or something like this, right? We've been just conforming of every single theoretical prediction that comes out of this theory, and I guess it's such a curious position to be in, because you don't know how to make new discoveries, right? When you basically get too good at it. And as I understand it from history, if you look back at the origins of quantum mechanics, for example, we had things like black body radiation, right, and the photoelectric effect, and this phenomena that couldn't be explained within the existing framework of classical physics, and so physicists were basically forced to develop this completely new view of nature that we call quantum mechanics. And right now we don't seem to have modern equivalents of anomalies like that. Maybe that's an issue. I don't know.
Yeah, I think it's a really good question, and I think to some extent we were sort of spoiled by the early 20th century in physics. So we went from the 19th century, where actually a huge amount of progress was made, and electromagnetism, thermodynamics, before that, Newtonian mechanics and all that sort of stuff. And it was really felt, we understood what was going on. And then in the late 19th, early 20th century, all these new phenomena start to appear that challenges the kind of established view of how the world works, and the kind of nature of the laws of physics themselves change. Like the idea that the world goes from being deterministic and classical to quantum mechanical is a huge shift in how we think about nature fundamentally. And so we kind of think about these big revolutions that happened, like in relativity, quantum mechanics, and the understanding of the substructure of the atom and new forms of energy and all this stuff that happened in the early 20th century. And it maybe made us think that that's sort of what science is like, but actually there's no reason to think that you're going to have continuous revolutions, right? Because, maybe the nature is like, the more you look, the more you find forever and ever and ever. But maybe that isn't what it's like. Maybe there is some limit in the sense that there are the laws, that there is the way the world works. And actually, maybe quantum mechanics and relativity between them are the correct descriptions of nature, and there is nothing that really supersedes them in a sense. There's also, I think, so this is getting a bit philosophical, but even the idea of revolutions in science is a sort of problematic one, because it's not true that when quantum mechanics and relativity emerged, that you just threw out all the old physics, like you got rid of classical physics. It's not at all, right? Thermodynamics, electromagnetism, dynamics, they're all still taught in universities for very good reason, which is they work very, very well in most cases. So if you're dealing with things that are not atomic scale and are not going near the speed of light, classical physics is great. And, a lot of our technology relies on understanding classical, not quantum mechanical or relativistic physics. I suppose the kind of change in that sense, I mean, what quantum mechanics represented was not just discovering, some new interesting phenomena. It was a kind of a reimagining or rethinking of the basic laws that govern the universe fundamentally deep down. I don't know that we'll ever have another revolution like that. String theory, perhaps, or some kind of quantum gravitational theory is the sort of perhaps the next kind of thing that you might imagine superseding quantum mechanics and relativity. But really that is it's not really an overthrow. That would be a kind of synthesis of these two ideas. I think that if there is another big breakthrough in the future, I think it's unlikely to be the sort of revolutionary transformation that we saw with quantum mechanics. It's much more likely to be some new particles that add on to the standard model that maybe make sense of the standard model. Maybe, the standard model is like in some ways very elegant, but in other ways slightly arbitrary, and we don't really understand why it has the particular forces that it does. Why does it have the set of matter particles that it does? So, if we find new particles, that may expand it in a way that we suddenly see the bigger picture and we realize there's some, deeper symmetry or deeper order to the fundamental particles. But that is a sort of an extension of the sort of physics we've been doing for 50, 60 years now. It's not a wholesale change in how we think about nature. And I would be surprised if we encounter another wholesale change of that type. And I think, there's a fundamental thing, like when a subject is new and young, there's lots of stuff you don't know. So you make discoveries very quickly, because as soon as you kind of start to look, you find things you've not seen before. There's a good example of this with like Galileo and the telescope. Telescopes were sort of originally used to for military purposes, looking at ships coming over the horizon. But very quickly, the instruments invented, people point it at the heavens and they start discovering the phases of Venus and moons around Jupiter. And, that leads to the shift in our understanding of our place in the universe and all the rest of it. But that is because no one had that instrument before. And we have had colliders and telescopes and all these other things for a century now, almost in some cases. So a lot of the low-hanging fruit has been plucked, and the stuff that hasn't been found is by definition much more difficult to find, because that's why we haven't found it already. So I think that sort of explains why progress maybe feels like it slows down or it gets more and more difficult. And, to get to the sort of next discovery, you have to make this massive push to some bigger machine, much more expensive, bigger telescopes, because you are looking for these much more difficult to find signals. And I think that's just an unavoidable consequence of having a very mature field, as you say. That doesn't mean it's a dead end, though. It just means that we have to keep pushing, and we may have to work very, very hard to get the next big discovery. But I have very little doubt that there are other things out there to learn, that we haven't come to the end.
In your most recent book, Space Oddities, that you've already mentioned, you talk about how small clues can sometimes lead to big discoveries, right? Not often, but sometimes that's the case. And when you notice this, tiny discrepancies, they may lead to great breakthroughs. And I was wondering if you could maybe tell the story of the anomaly Mercury's orbit, because I think it's such a wonderful example of how these tiny discrepancies can basically end up transforming our understanding of the universe.
Well, the problem with Mercury is really interesting. So this is the 19th century. Now, I'm going to forget the date, but I think we're talking 1859, something like that. I'd have to go and check
It
my book.
doesn't matter.
But it's about then. But basically what had happened in astronomy, there had been this problem for a long time with the orbit of Uranus, so the 7th planet in the solar system, in that it wasn't appearing in the sky where it was expected to appear according to Newton's laws of motion and of gravity. And this French astronomer, Leverrier, basically realized that you could explain the anomaly in Uranus's orbit if there was an 8th planet outside the orbit of Uranus that was pulling on Uranus and changing its orbit. And so he predicted where this 8th planet should be, and then astronomers looked and they found it, and that was what we call Neptune. So this was sort of an anomaly in the orbit of one planet that led to the discovery of another. Then there was another problem with the orbit of Mercury, so the closest planet to the sun, in that it kept, again, not conforming to predictions of Newton's theory. And in particular, it seemed to be orbiting the sun slightly faster than you would expect. And Leverrier thought, well, maybe it's the same explanation. So he predicted perhaps closer to the sun even than Mercury is another planet. And this little planet, you maybe wouldn't have seen it because it's hidden in the glare of the sun. It's very close to the sun, so it's very hard to see because the sun is so bright. But this could be tugging on Mercury in the same way that Neptune was tugging on Uranus. So Leverrier, he writes a paper predicting the existence of this planet, which he names Vulcan, after the Roman god of the forge, Hephaestus, I think, in Greek. And there's an amateur astronomer called Edmond Lescarbault. So he lives in this village outside Paris, a few hours outside Paris. He's actually a rural doctor, looks after the kind of aches and pains of his local residents. But he's also an amateur astronomer. So he has this little observatory that he's built on the back of his house. And one day in, I think it's March 1859, he is looking through he's looking at the sun using his telescope. So he's taking a telescope, pointing at the sun, projecting an image of the sun's disk onto a piece of card. And he notices on this image, there's a black dot that appears on the edge of the sun and then moves across the surface of the sun and then disappears off the edge. And this is really surprising. So this looks a bit like what we call the transit of a planet. So we get these things called the transit of Venus, the transit of Mercury, where Mercury or Venus cross the disk of the sun. So they pass in between us and the sun. And they appear as a little black dot crossing the surface. And this is not, this observation that Lescarbault makes doesn't correspond with the predicted transit of any of the planets. So he doesn't really know what it is. He wonders if maybe it's a sunspot, not really sure. Makes a note of it in his little logbook, but then sort of forgets about it. And then much later that year in December, he's reading a copy of a astronomical journal where Leverrier has published this prediction of the planet Vulcan. And he suddenly wonders, oh, maybe I've seen Vulcan. Maybe I've seen this planet that Leverrier predicted. So he writes to Leverrier just before Christmas. And Leverrier is so excited by this letter from saying, I've seen this strange thing on the sun, that he gets immediately on a train, goes down to this village outside Paris, and is bangs on Lescarbault's front door. So this is New Year's Eve now, just before the end of the year. And Lescarbault is really startled. Leverrier is this very grand figure. He's the in charge of the Imperial Observatory in Paris. He's famous for predicting the existence of Neptune. And he basically submits Lescarbault to this really fearsome interrogation, and what have you seen? Gets him to show him astronomical equipment. He inspects his measurements. He then goes around the village and gets character witnesses from Lescarbault's neighbors to check he's not a confidence trickster. But by the end of the day, he basically goes back to Paris, concluding that Lescarbault, this amateur astronomer, has seen Vulcan, has discovered Vulcan. And the discovery is announced in the new year. It's a great fanfare in the press. And Lescarbault is given the Légion d'honneur, one of France's highest honors for the discovery of this planet, Vulcan. And it's a massive story. And then astronomers Leverrier then predicts, based on Lescarbault's observations, where will Vulcan next appear? So when will you see it crossing the sun again? And astronomers look, it doesn't show up. And they try again, for decades, actually, through until the early decades of the 20th century. And eventually, by around 1910 or so, people conclude that this planet Vulcan actually doesn't exist at all, that it must have been something else, whether it was like a fly on the telescope or a sunspot or who knows. But it's not a new planet. But the problem with Mercury's orbit is still there. Mercury is still not behaving as it should. It still doesn't turn up in the sky when it should. And it actually turns out that this effect is a clue to one of the biggest revolutions in our understanding of the universe, which is Einstein's general theory of relativity. So in the early 1910s, Einstein is working on this new theory that basically takes Newton's theory and supersedes it and describes gravity rather than as a force, as a consequence of the curvature of space and time. So Einstein thinks of space-time as this sort of fabric that can be bent and squashed and stretched. And in his theory, gravity actually arises because massive objects like the Earth and the Sun bend space-time around them, and objects roll effectively around this depression in space-time, which is why the Moon orbits the Earth and why the Earth orbits the Sun. And Einstein spends 7 years putting this theory together. It's his kind of masterpiece. It's very difficult mathematics. He struggles with it for a very long time. But in 1915, he is sort of getting close to being able to reveal his theory to the world. And the first thing he does once he has a version of this theory that he can make calculations is he calculates the orbit of Mercury. And he finds that his theory accurately describes the orbit of Mercury when Newton's theory didn't. And this is a kind of major boost to Einstein because it actually describes being so excited he had heart palpitations and had to lie down and, for some hours afterwards. And it's the piece of evidence that really convinces much of is the first piece of evidence really that this really radical new picture of gravity and space-time and the universe is the correct description, and that Newton's theory, which had been around for 300 years, has been, overturned. And general relativity is still our best theory of space-time, and it led to black hole, understanding of black holes, the Big Bang, gravitational waves, all these sort of modern phenomena that we're still investigating. The clue to that, though, was in this funny little deviation in Mercury's orbit, and this is like a 1 in a million deviation. It's very small. It's a small effect, but if by following these sorts of details, you sometimes get to these big discoveries.
I remember I was talking to Kip Thorne, Nobel laureate in physics, and it made me think about like that amazing LIGO experiment and the fact that both the LHC, for example, and the LIGO, they required an extraordinary amount of effort, right, to build, and a huge financial investment. Perhaps most importantly, they depended on international collaboration because scientists from many different countries working towards a common goal. And as I know, by the time that these gravitational waves were first detected, the LIGO involved over 1,000 scientists, and the LHC obviously has thousands of scientists working on various projects. And I love that aspect of science and find it kind of inspiring. Maybe you can add something to it.
Yeah, I mean, I think that's one of the really important aspects of modern science or big science. This thing that science is universal. That actually, whether you're in the UK or the US or Ukraine or in China or Japan, we're all trying to understand the same questions. Like physics is the same, doesn't matter where you are in the world. It's a kind of common language. And, in some sense, science has been a kind of international pursuit for a very long time, going back way before we had big particle accelerators or big telescopes. You had the international scientific community and people reading each other's articles and their results and building on the work of others abroad and collaborating. And it's kind of interesting when you read back the early history of physics in the 20th century, around the First World War, for example, where you have, for example, in the UK, you have Ernest Rutherford at Manchester and Hans Geiger, who is a German scientist who works with him in Manchester, but then they all find themselves on opposite sides of the war, having been colleagues, but, these kind of relationships sort of transcend to some extent what's going on geopolitically. And I think that's one of the very important aspects, particularly in the world now, which is so kind of fractured and unstable, that these scientific projects do bring people together. And that was sort of by design to some extent. After the Second World War, one of the reasons for establishing CERN in Geneva was to kind of rebuild a coherent European community of scientists, which had been, fractured and scattered across the world as a result of the war. Many people went to America, and it was trying to kind of bring people back to Europe to work together. And I think that's one of the great pleasures and privileges of working somewhere like CERN, is you get to work with people from lots of different countries, different cultures, speaking different languages as their first language. And I think that kind of enriches the science as well, because you have different ways of thinking about a problem that actually come together and allow you to solve it in a way that maybe be more difficult in a kind of monocultural environment. So that there's a kind of, it benefits the science, but I think also has a very important role to play in bringing people together and having governments collaborate and work together. I mean, it's interesting if you look at the International Space Station, even over the last few years, you still have Russian and American astronauts working together to keep the space station in orbit and maintain it and so on. Even when things were particularly tense between the US and Russia a few years ago. So,
It does seem like there is something really unique about the way that we do science, and how scientists are able to figure out what's true about the world. Because you describe that process so beautifully in your books, especially in Space Oddities. Maybe you can say a few words about that.
What makes science different? I mean, I suppose the first thing to acknowledge, science is a human activity, right? And humans are flawed and they make mistakes. And I think in many other subjects, it kind of points of view matter and opinions matter a lot more. And in science, your opinion doesn't really matter in the end, right? What matters is what is the way nature is. And the scientific method, the idea that you do experiments, you make measurements, you test your hypotheses, even though you may get wrong results now and then, or you may get people who behave fraudulently. On the whole, you will get found out, and in the end, knowledge increases. And it's not something that's driven, as much as historians of science or philosophies of science might say this. I don't think on the whole it's driven by fashion or by opinion, because if someone can't replicate your experiment, they can't replicate your experiment, and your result will never be taken seriously. So it's kind of self-correcting, and the laws of physics or the laws of nature or the phenomena of nature are universal. They're the same everywhere. It doesn't matter where you are. In science, you want to discover something, you want to find out new stuff. That's why we're in that business. So it's very easy to sort of see an effect and think, oh, I've made a big breakthrough. But you have to treat your own work as well as everyone else's with a healthy dose of skepticism, because it is very easy to make mistakes, and it's very easy to trick yourself into thinking you found something when you haven't. So that kind of skeptical approach, not taking things at face value, really digging into the details, really, really convincing yourself. And that's where most of the work in what I do comes in most scientific work. It's really, really testing at, to sometimes a kind of what seems like an absurd level, how your methods have been put together, what your results are showing. Because it's only when you've really, really scrutinized everything that you be confident in what you're presenting.
You mentioned a bit about what may come next after the LHC, the Large Hadron Collider. I would love to know, where we are in that process today. Is this next generation collider, in your view, something that's likely going to happen, or are these plans still largely being debated? Maybe some of the biggest challenges standing in the way. Does it all come down to funding, or maybe there are some other challenges?
So there's been this process that's been going on recently in Europe called the European Strategy for Particle Physics, which is looking at the future options for what we'll be doing in particle physics for the next several decades. And first thing to say, the number one priority is exploiting the LHC, so making sure we get as much as we can out of the LHC. But people are obviously also thinking about what comes afterwards, and you have to, because these projects take decades to design and build and operate, so you have to think way ahead. And the project that the community has kind of coalesced around is this thing called the Future Circular Collider, which would be a successor to the LHC that would be built in the 2040s and start operating in the late 2040s. So we're talking a sort of 20-year time horizon from now, more or less. And the purpose of this machine, well, first of all, to give you a sense of scale, it would be at CERN in Geneva. The LHC is 27 kilometers in circumference. This thing will be 90 kilometers in circumference, so more than three times the length. And its first version will be an electron-positron collider. So it will collide electrons with their antiparticles in order to create lots and lots of Higgs bosons. And the idea of this machine is to really, really understand the Higgs, because the Higgs is the sort of central character in some sense in modern particle physics, is the center of the standard model, makes the whole thing work, but it in itself is deeply mysterious, and we still don't know a lot about it. We don't really know whether it really gives mass to the basic particles that make up ordinary matter, and we don't know whether it really is the Higgs boson that was predicted by Peter Higgs and others in the 60s, or whether it's something more exotic, whether it's made of smaller things. It's also bound up with issues like, dark matter, the origin of matter in the universe, etc. So understanding the Higgs is kind of the primary goal of this machine. That's the first version, and that will run, if it's built, through till the sort of 2050s. And then there's an even more ambitious thing after that, which is in the same 90-kilometer tunnel, you take out the electron-positron machine and you put in a proton-proton machine like the LHC. So this would be like a very large hadron collider. And this would be a very high-energy machine that would explore the highest energies we can reach and try to discover new particles directly. So that's the kind of that is a machine for the 2070s. So we're talking half a century in the future, basically. So yeah, where we are, like the European physics community has kind of, or particle physics community has coalesced around the FCC as being the next big project for CERN. And CERN are kind of scrutinized. There's been a feasibility study. There's a clear site for where the ring will be. They've talked to all the local authorities about where they would build the facilities around the Geneva area, et cetera, et cetera. So there's been a lot of detailed work that's been done, budgeting, project planning, et cetera. And what really needs to happen now is like CERN are considering all this information, and there is a plan to sort of give a go, no go to the project in 2028. So in a year and a half or so from now, 2 years from now. So we should know by then whether the CERN are really going to push for this thing. But then, of course, the challenges are persuading governments to invest in another big collider. And I think, and also unifying the scientific community more generally around this project. And there are still people who don't necessarily agree that this is, the thing that we should be building or spending money on. And so that there's work in the scientific community, there's work in government and in the public, and sort of explaining why this thing is useful, why it matters, why we should build it, and what the benefits will be. I don't know, as to whether it happens sort of above my pay grade. I think one thing is kind of obvious is that the world is, going through a period of like pretty high instability. And there's a question about, do governments have the appetite, the long-term stability, can they justify the outlay on what would be an expensive project? I mean, the cost of this thing, the total program, we're talking 25 billion Swiss francs, but that is spent over half a century. So it's spread over a long period of time. But nonetheless, it's a large amount of money. So, given what's happening with national budgets and cuts happening in a lot of countries, and in the UK, actually, we're facing pretty severe cuts to fundamental physics, astronomy and particle physics are facing 30% cuts to their budgets. And actually, I was just at Parliament yesterday trying to persuade MPs that this was a bad idea for various reasons. But you have to think, well, in that kind of climate, will we be able to make a compelling enough case that this is worth investing in? And I think it is worth investing in for lots of different reasons, not just to do with the science, but also to do with training the next generation of highly technical people, physicists, computer scientists, engineers. It's about inspiring the next generation. It's about the investment in high-tech industry, in development of spin-off technology, et cetera, et cetera. But all of this has to come together. So I honestly don't know. I think there's a chance. It's by no means certain. So we'll see. We'll see. Hopefully in a year or two, we'll have a clearer picture about where this is going.
In our first conversation, when I asked you about religion, you said that you're not particularly a religious person, right? When you, for example, look up at an sky and it happens to be like a clear night, where you can see lots of stars, basically. And when you put together like Einstein's general relativity and quantum mechanics, when you put all this into the mix, is it really all there is to it, or how can this yield such a magnificent universe? Just all by itself.
That's the question we're trying to answer ultimately, right? Is, how do these basic laws and these basic particles come together to make this really rich and complicated and beautiful universe that we live in? That's one of the big mysteries. And, we don't know the answer to that. But we have learned a lot, right? we can speak with some confidence about the origins of the universe going back to a trillionth of a second after the Big Bang, or as far back as we can really realistically think about the history of the universe. And that's kind of extraordinary, right? You know, if you think 100 years ago, we didn't know anything really about the history of the universe. We didn't know if it was eternal. We didn't know whether it, began. I mean, one thing we did know is it wasn't created 6,000 years ago on a Tuesday, as the Bible said, because of radioactive dating of rocks that showed the Earth was much older. We don't have all the answers, obviously, but we've learned a lot. We know a lot more than we did, and there's still things to unravel, but that doesn't mean that you need a supernatural explanation. And we may find that actually there is a limit to what we can know, that we will eventually run up against unmovable barriers due to the laws of nature that say, well, you're not allowed to know, you cannot know what happened before this time, or you cannot know what goes on at this distance because, signals from that time or distance can never get to us, or we can never build a collider big enough to get down to the scales to probe quantum gravity. So maybe we'll never find the ultimate answer through science, but that doesn't mean you need to invoke God or gods or anything else to understand where we are in the universe.
Yeah, but I just find it amazing that, in some ways, very simple equations that you can literally write them down on a t-shirt, right? That they, over the course of billions of years, they can somehow yield, like you and me, and talking here, and, there's conscious beings, like trying to make sense of it. So
yeah, that's wild. I agree. Yeah, it's crazy. I would say it's not the equations, though. I mean, the equations are just a description of nature. But these things we observe seem to obey these physical laws, or at least approximately they obey them. But yeah, I think that is a deep mystery. How do quarks and electrons make a human brain? I mean, it's kind of crazy that the actual laws that do, if you look at how these things behave, they're very simple, really. Electrons and quarks, they have very few properties. They obey very, straightforward laws, really, even though physics seems complicated. It's much simpler than the world. Like, the world is way more complicated than physics. So the fact that you can get all this complexity and richness from such simple ingredients with simple properties is kind of mind-blowing. Some people would argue that, that kind of reductionist approach to science is wrong, that actually you can't think of quarks and electrons as giving rise to a human brain. I mean, certainly quantum field theory is not a good way to think about consciousness. I mean, that's the wrong kind of science. But I do, at the heart, think that all the phenomena we see at macroscopic scales has its origins in the microscopic. It's not the other way around. But, you're never going to be able to explain how a human brain works using particle physics.
The final question I want to ask you is, I'd love to know if you could share maybe what you're working on now. Some of the plans for the next few years. Maybe you're thinking of another book to write, or maybe there are some science projects that you're particularly excited about. And maybe it would be lovely if you could tell us a bit about the two books that you've already written, right?
Well, thanks for inviting me to give them a plug. Yeah, I mean, I've written two popular science books. The first one was called How to Make an Apple Pie from Scratch, which is about the quest to understand the origins of matter. So, what is the world made from and how did it get here is the question the book asks. And it kind of takes a tour through our growing understanding through kind of early chemistry right the way through to the Big Bang Theory and quantum gravity, and with particle physics in between. So it's kind of, in some ways, that book is the story I've always wanted to tell. It's the kind of grand history of how we figured out how the world is the way it is. And of course, that story is not finished yet. And then the other book is called Space Oddities. We sort of alluded to it, which is about these strange anomalies that have cropped up in physics and astronomy in the last few years, and to what they might be telling us about the next step in our understanding of that journey, really. But yeah, I mean, at the moment, my main focus really is on physics. So we've just finished run 3 of the LHC. I work on LHCb. We've got loads of data to analyze, lots of measurements to make. So that's taking up a lot of my time. I would like to write another book. Honestly, I actually have an idea for a sort of a novel rather than a nonfiction book, which is a bit of fun. I don't know whether anyone would ever publish it, but I always used to like writing stories when I was a kid, and I've sort of come back to it a little bit recently. Although again, it's finding the time to actually get down and do it is the difficult thing. So that's probably the next thing in terms of writing I really want to work on. I have had an idea for another nonfiction book in the back of my mind for a while, and that would be a book about nothing, so about the vacuum. But it's very embryonic. I haven't really developed it yet, but I need a bit more time. I need an extra like 3 or 4 days in the week to do all these things. That's the problem I always find. But yeah, but it's sort of the physics is the focus at the moment, along with a few other fun sort of side projects as usual. But no books in the works yet. But maybe in the next few years, we'll see.
Thank you very much for your time. I must say that the way you talk about physics is like music to my ears. So.
Oh, well, thank you. That's very kind. That's very kind.
Yeah, and so I've always looked at your writing and your public talks as a great example of how this subject should be communicated.
Thank you for the kind words. It's been great talking to you again, and I'm sorry it took me so long to get back to you this time, but life gets in the way sometimes. But yeah. I hope the podcast goes from strength to strength. It's been really fun talking to you again.